My name is Samuel Blaterschut and I will be presenting the project Engine Belt Vibrations on behalf of Group I. These are my colleagues, without whom the project would not have been possible. Let us get into it. The subject for research on a cam belt or a timing belt of an internal combustion engine. Timing belts are different from normal flat belts because they have a constant transmission ratio, not dependent on torque. This is due to the fact that the mechanism of power transmission is geometrical interference and not a frictional one. Thanks to this property, the type of belt is also called synchronous, and it's suitable for applications in which sliding is not acceptable, such as for moving a camshaft in an internal combustion engine. This also makes it an interesting topic to analyze regarding vibrations. So, what do we do? The analysis of the belt is made up of the following activities. A theoretical research will be performed, aiming primarily to obtain the system characteristics. For the other objectives of the research, I will come back shortly. To validate, understand and visualize this model, a Matlab model will be constructed, which will utilize numerical methods to approximate the solution of the system. Most notably, the system characteristics will be examined for different speeds and the response of the system will be visualized for an application of a point force at the midspan. Let's first characterize and simplify the model. The belt will be modeled as an actually moving beam, which is simply supported. This model of an Euler beam is based on the model developed by nonlinear dynamics and bifurcations of an actually moving beam by Pellicano and Vesteroni. A more mathematical formulation of the dynamics of the belt will follow shortly. For now, I would like to point out that W is associated with the axial motion, while U is representative of the longitudinal motion, which is now only considered to build the equations of motion, but more on that shortly. Out-of-plane motion is not considered. Also, the density and the cross-section are considered to be constant throughout the belt. With this model, what are our objectives? First, the system characteristics need to be defined. Specifically, the natural frequencies need to be represented versus actual velocity, hereby defining the critical speeds. Subsequently, the mode shapes, which will be complex, but more on that later, are found on and the model oscillations are visualized. Ultimately, the transit response is studied for the system, which is excited by a point force located at the midspan. The theoretical approach. The system can be modeled as a partial differential equation. To obtain this equation and to solve it, a couple of steps need to be undertaken. I will introduce them here shortly and afterwards I will give a dedicated clarification. First, the equation of motion is found using Hamilton's principle. Second, the Galerki method is applied. After this step, the natural frequencies can be approximated and plotted for the differential for different actual speeds, which will turn out to have a significant effect. Once approximation has been made, also the mode shapes will be plotted. Lastly, the response of the belt to a point force at midspan can be visualized by modeling the force as an impulse, which I will come back on shortly. So, the Hamilton's principle. To obtain the equations of motion, Hamilton's principle has been utilized, which states that as the system moves between two time instances, it does so along a trajectory that makes the action integral of the Lagrangian as small as possible. The Lagrangian is defined using the potential and the kinetic energy of the system. The kinetic energy is obviously related to the speed and the mass, which is defined by the cross-section and the density of the belt. Notable here is in the potential energy formula that it's defined using two-term nonlinear strain, which has two components as the name says. Two components on both directions of motion. Eventually, these equations of motion are the result, for which I will spare the derivation. The upper one is the equation of motion for the longitudinal direction, and the lower one is for the transverse direction. Here, the difference between a continuous system and an n-degree of freedom system becomes prevalent, as we obtain here a partial differential equation instead of an ordinary differential equation. In addition to the equation of motion, also some boundary conditions are applied, which entail that the displacement in both directions is zero for the supports, hereby making these geometric boundary conditions. To simplify and generalize the model, the following non-dimensional parameters are defined. After these considerations, we are actually going to simplify the system even further. By disregarding the nonlinear terms and the fast dynamics in the longitudinal direction, we are left by this one quite elegant equation, which now is only based on a transverse motion. Like I mentioned earlier, the Galerkin method has been applied. The Galerkin method can be an excellent method approximating the solution, making use of a projection with a trial function which closely resembles the eigenfunction. Namely, an eigenfunction for a simply supported, non-moving Euler beam was used. Both terms of this equation are multiplied with sin k pi x for k is 1 until n. The result is subsequently integrated over the domain 0 to 1. This step, which transforms an almost impossible to solve equation to an approximation which can be solved, making use of orthogonality conditions. Hereby, a partial differential equation is transformed into an ordinary differential equation. To achieve good accuracy with little computing time, n has chosen to be 8, but for now, that's not important. This produces a finite dimensional dynamic system in the form of a differential equation, and this can be written into compact form, which you can see on your screen. Then a translation is made to work in the model space by defining the vector p, the force vector, and the matrix A. Ultimately, by imposing the force to 0 and with the help of the newly built matrix A, the eigenvalues and vectors can be defined. So now we're getting somewhere. The eigenvector and the eigenfunctions are defined as such. With the use of the previously defined Vf, the critical speeds can be found, which we will see in a moment is backed up by the plots of the natural frequencies. To find the model oscillations, the free problem needs to be solved, and P, which also includes Q, need to be found. This can be done numerically. Finally, to obtain the motion, in this case the model oscillation, the coordinate Q is multiplied with the eigenfunction. So now we have a model which produces results to the free vibration condition. The last step is to apply a force, a point force for our case. The point force is defined as a half sine wave to mimic a realistic impulse excitation. To implement it in our system, the force needs to be projected and put into vector form. Then P and Q can be calculated and a response will be obtained. Our model is finished. Let's now implement it to validate it and visualize some results. For the numerical model, some parameters need to be chosen. This is done on the basis of a real-world example. The well-known widely used Fiat fire engine has been chosen. As can be seen, this timing belt has a relatively simple design and closely resembles our simplified model. A relatively low power outputting model with a maximum speed of 50 meters per second has been chosen, because for higher power and speed applications, timing belts actually tend to be exchanged for gears, which prove to be more reliable at high speeds. These are the associated values for the parameters, however I will not dwell too long on this. So now the numerical implementation. For the numerical implementation, a Matlab model has been constructed. As I said earlier, the Galerkin method implies that we implement an approximating solution. The n value for this is 8. I will not dive too deeply into the Matlab model, but the following things need to be explained for the results to make sense. The model oscillations are plotted for 10 different time values to better visualize their behavior. For the response to a point force, a speed of 10 meters per second for the belt has been chosen, as this lies well within the working range of the belt. Like I said earlier, the force is modeled as a half sine wave to mimic an impulse. Lastly, the model is validated using the same parameters that were used in the references, and the results we obtained were in agreement with the results from the actual references, thereby validating our model. First up are the natural frequencies. They are plotted against actual velocity, and the behavior we can see is interesting. First of all, the critical speeds are shown to be around 100 meters per second. This is the critical area, which, for above this, unstable dynamic behavior can be witnessed for the beam. In the subcritical area, the natural frequencies 8, because we chose n to be 8, tend to decrease for an increase in actual velocity. The highest two do not share this trait, but this anomaly can be explained by the inherent numerical error produced by our model. It has to be mentioned that the prescribed working range of the belt is up to 23 meters per second, associated with 8000 RPM, and therefore not even close to our critical speeds. The earlier mentioned formula to calculate the critical speeds has been validated by the graphical result, as we can see by these values that the natural frequencies do indeed decrease to 0. Next, the eigenfunctions are plotted for two different speeds. Again, we have 8 because n we chose to be 8. First, we can denote that the eigenfunctions turn out to be complex. Second, the dependence on the speed is noticeable. Both speeds are chosen to be in a subcritical range, but already at 75 meters per second, some strange phenomena start to occur. This has to do with the way these eigenfunctions are built. As I've shown in the slide about theory development, the eigenfunctions are built by a summation of 8 different multiplications of the eigenvector with the base function. At low speeds, the model oscillations are built predominantly by one base function. At higher speeds, the other base functions start to have a larger effect, and therefore create a more complicated oscillation. These are the model oscillations for two different speeds. It obviously follows the same trends as the eigenfunctions because it follows the same trends as these are the eigenfunctions multiplied for the coordinate q. We plotted it for 10 different time values, as can be seen. Noticeable is that the location of the nodes actually change for different time values. Note only that, also the shape of the oscillation will change, not just the amplitude. This is due to the complex nature of the eigenfunctions. Lastly, we have the point force application. The force excites a vibration to the system, and because the system is without damping, this oscillation is maintained. The response is examined after the impulse. Left is the slowed down response to visualize and understand how the belt is actually moving. To conclude, a continuous system has an infinite number of natural frequencies. However, as for this model approximation is made, only the first 8 are analyzed. The actual speed strongly affects the natural frequencies, eigenfunctions, and model oscillations, in the manner I just explained. As we can judge from the plot of the natural frequencies, within the working range of the belt, instabilities due to critical speeds will not take place. The model proved to be working and reliable. It would be a waste if we didn't utilize it for something other than the prescribed applications. Therefore, we decided to examine the other side of the belt. Because timing belts transfers load by geometric interference, it has a strongly tight and slack side, hereby differing between the two sides in the amount of tension which is present. Up until now, the tight side has been the one which was examined, the results of which can be seen on the left. However, if we take a close look at the slack side of the belt, it can be noticed that the critical speed lay around 50 meters per second. An interesting find, which could explain why the manufacturer prescribes a maximum speed of 50 meters per second. A last calculation has been made for which we checked our find, which stated that for higher power and speed applications, a belt as this one would become unsuited. To cope with an increase in power, the belt would have a greater cross-sectional surface. Therefore, two other belts were examined with greater cross-sections. The results visible right now broadcast that for a bigger cross-section the critical speeds tend to become lower, which Wood Validator found. All in all, we are very pleased with our outcome. This was our project. Thank you for listening.